Hi everyone, welcome to another episode of McLaren Substitute Teacher, where we reveal the secrets of Formula One. Pay close attention and you could end up here at the racetrack designing, building and running a Grand Prix car. But don't think about driving one, that's my job. Today's lesson is brought to you by Matilda, a specialist in materials engineering. Pens and paper at the ready.
Hi, I'm Gemma and I'm with this week's McLaren Substitute Teacher. Why don't you introduce yourself?
Hello, my name's Matilda and I'm one of the materials engineers here. And today we're going to talk about materials properties and their selection. So basically how we decide to use which materials where on the car and why.
So an F1 car uses lots of different materials?
Absolutely, a lot. And understanding the materials properties from the atomic level up helps us design and build a safe, reliable and hopefully fast car.
And also a very competitive one.
That's the aim. But there's a saying in F1, to finish first you have to finish.
Okay, while the pit lane is open, let's get started. Okay, let's talk material properties.
So materials are usually grouped by their chemical composition and the associated chemical properties. When selecting a material for an application, we also need to take into account the mechanical properties, which more often than not are related to their chemical properties.
Okay, so what are the different types of material?
So one way of classifying the materials is by putting them into broad groups. For example, metals, ceramics, polymers, and obviously composites. In today's lesson, we're going to consider some properties of materials and the way that they affect our F1 car.
It's time for some heavy metal.
Actually, it's surprisingly light. Oh, that's an aluminium alloy. And when we load different alloys, they bend by different amounts. This is because of differences in the stiffness, or what's called the Young's modulus. That's a measure of how easily something can bend or stretch.
Do you know what? I think I've got an album by Young's Modulus.
They are a band, but I think the scientific term came first.
Okay.
It's really important an F1 car keeps its shape on track. If the stiffness of the materials were too low, the parts would constantly wobble under different loads, and that would make the car unpredictable and hard to drive. It's probably also going to be a slow car and might not meet the FIA rules. When parts are loaded, they bend. However, if we stay within the elastic limit of the material, when unloaded, the parts return to their original shape.
Like a piece of elastic.
Like a piece of new elastic.
Okay.
It's not quite true for old rubber. But when a material is bent and we go beyond its elastic limit, it won't return to its original shape. The stress at which this occurs is called the yield strength of the material. If you go beyond this point, the material has deformed plastically, and that change is irreversible and permanent.
Or to put it another way, completely busted.
Even with all the loads removed, the part is not going to return to its original shape. Parts of the car were too stiff, or the yield strength was too low, the elastic limit would be constantly exceeded, which means you'd end up with
one very battered car.
And it doesn't end there. Once you've gone beyond the yield strength, continuing to load a part will only cause it to deform further and further before a catastrophic failure. That happens when you reach the UTS, the ultimate tensile strength of the material.
So that's breaking point.
That's breaking point. And we don't mean the 50-metre board pre-corner.
So how do we stop materials exceeding their UTS, their ultimate tensile strength?
Well, like all things in F1, we do a lot of testing. To gather this data, we can use a tensile test to produce a stress-strain curve.
Ooh, I feel an equation coming on.
So, stress equals force over area. Essentially, it's a way of us normalising different forces for different sizes of components if everything else is the same. And then the second equation we're going to look at is strain, which is equal to the change in length, so we'll call that delta length over the original length. I'm now going to draw a very generalised stress-strain curve to show what we might see for a metallic tensile test. We need to remember that all materials are different and the curve produced might not look like this at all. In this first region of the stress-strain curve, the material obeys Hooke's law. In this limit, the ratio of stress with strain gives the proportionality constant known as Young's modulus. And then we see the limit of proportionality. Beyond this, we can still return to the original position when the load is removed, but we might reach the elastic limit pretty quickly, and then plastic deformation starts to appear. At the yield point, we then move into plastic deformation. Beyond the yield point, we then have the ultimate stress point. That's the maximum stress that a material can endure before failing. And then we move on from this point and we get fracture or breaking point. That's the ultimate tensile strength that we referred to earlier.
So this curve stops your car from going to pieces?
Unfortunately not, but it is a start. What this curve doesn't tell us is the effect of repeatedly loading and unloading a material. And when the car is going around the track, the changes in loads mean that many of the failures we see are fatigue failures. These happen over many cycles of loading and unloading, or loading and then loading in the opposite direction, which causes cracks to grow and expand.
So what do these cracks look like? Are they easy to spot?
They're not easy, but there are a few telltale signs. We use our scanning electron microscope to examine fracture surfaces at high magnification and high resolution. If you look at this image, you can see a typical fracture surface from a fatigue failure. The beach marks show crack growth.
Oh, not good.
Never ever good. You're heading for the pits, or even worse, the crash barrier. Ready for another equation?
Oh, yes, always.
We've talked about elasticity. Now, let's talk about density.
I know this one. It's density equals mass over volume.
The material with the highest density that we use on an F1 car is tungsten. It's used for ballast, as the high density means only a small piece is needed and can be packaged in an aerodynamically friendly way.
Have we got a sample here we can look at?
Of course we do. Here's tungsten, the high density material.
Whoa! Gosh, that is so much heavier than I was expecting.
Now compare it to some low density aluminium that we were using earlier.
Yeah, it's so much lighter. Whoa. Wow.
Thanks to density, a tiny piece of tungsten can outweigh a big lump of aluminium.
But an F1 car wouldn't get far made from tungsten and aluminium.
You're right. So let me show you two other materials which play a crucial role in the construction of the car. Steel and carbon fibre. So steel is the preferred choice of material for gearbox internals, whereas carbon fibre is the #1 material for crash structures. When a piece of carbon fibre fails, millions of fracture surfaces are created, and this requires energy. Therefore, the energy from a crash is absorbed by the failing carbon fibre, and it minimises driver injury.
We've discussed elasticity, yield strength, fatigue, density, and fractures. Are these all the material's properties?
We've barely scratched the surface. There are so many other properties that we have to consider as part of the selection process. Compressive strength, magnetic permeability, thermal conductivity, electrical conductivity, machinability. The list goes on and on.
And so does Formula One. I mean, as a sport, it's unbreakable. So let's leave you with a little bit of homework and a few brain teasers. We've shown you the advantages of carbon fibre, how it has a lower density than steel and absorbs a huge amount of energy in a crash. So why don't we use carbon fibre for every component? Can you think of any possible disadvantages?
And what other properties do we have to consider when choosing the best material for an application? Maybe you can think of something we haven't.
Post your responses in the comments section on YouTube or on Twitter and Instagram using the hashtag McLaren Substitute Teacher. And who knows, maybe one day you'll be a valuable property at McLaren. School's out. Thanks for watching. Bye.
Bye.